Hey, AP Statistics. So continuing section 9.3, putting together the one sample t-test for mu. In the last section, or in the last bit, we looked at kind of the process of doing, but now we got to get that all together, and it's going to feel very similar. State, plan, do, conclude. So state the hypotheses you want to test and the significance level, and define any parameters that you want to use. Plan, identify the appropriate inference method, and check conditions. Then you actually do it. You perform the calculations, you give the sample statistic, the X bar, calculate the standardized t-test statistic, which should be T, if this is a sample t-test, and then find the p-value for it using your TCDF or your table technically, and then conclude, make a valid conclusion about the hypothesis in the context of the problem. All right, and then they're kind of reminding us here there are 3 conditions we must check to meet the formula. And the standardized statistic to be valid, one for each of the 3 components of the formula. So X bar has got to be right based on our random condition, that's not biased. So that's a good estimate. The normal condition needs to be met, the large sample needs to be met, so that we can actually use the t distribution is based on that normal distribution. So I know it looks like t here, but that's, so we're using an appropriate t distribution, but kind of based on normal sampling distribution. And then the 10% condition, so that we can check for independence. We're sampling without replacement, and so that formula only works under those conditions. So supposing the conditions are for the test are met, we're going to be performing a test of the mu equals mu naught. We compute that standardized test statistic, and then find the p-value by calculating the probability of getting a t-test statistic like that, this large or larger, in the direction specified by the alternative hypothesis with the degrees of freedom n-1. So if it's a one-tail test to the right, if our alternative is mu greater than, we're going to go a right tail. If it's mu less than, we're going to go a left tail. If it's a not equal to, we got to go both tails. And so whatever our t is, we go area above it and then double it, or below it and double it. All right, so putting one all together, an example, the level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter for all those. An average dissolved oxygen level below 5 milligrams puts water per liter, puts aquatic life at risk. So we have all that data. We type it into our calculator if we were doing this, and you can try and do that as we go along. So do the data provide convincing evidence at alpha level 0.05 significance level that aquatic life in the stream is at risk? Seems like a simple question, but that is a full-on state, do, plan, conclude. If it's asking it's significant, do they provide evidence? We're doing a full-on significance test. So, and then the second question will come back to with errors. So we want to test mu equals 5 versus less than 5. So our null hypothesis is not any different, nothing special going on, and then our alternative is less than 5. We're trying to find significant evidence that is less than 5. Where mu is the true mean dissolved oxygen level in the stream using alpha level 0.05. So we've stated our significance level, we've just stated our parameter, defined our parameter, and our hypotheses are set up here, our null hypothesis and our alternative hypothesis. So then we plan, we name what we're going to do. This is a one sample t-test for mu. We have to check our conditions. We have our random condition. We did do random locations, kind of a weird population. The 10% condition is a bit weird too because of that. There are an infinite number of possible locations along the stream, so really it isn't necessary to check the 10% condition. And then the normal / large counts condition, we're going to have to look at our data, and so they did a little histogram here, and it looks good. That's roughly symmetric, no major skew or outliers. So then we actually do this thing. We have to calculate X bar and S by typing in that data into our calculator and running one variable statistics. X bar minus the mu naught is 5 there, divided by our sample standard deviation over the square root of the sample size. And so that will give us our t-test statistic. This was a one-tail test and the degrees of freedom are 14. So we'll do in our calculator TCDF from -infinity up to that bound of, sorry, I'll try this again, TCDF from -infinity up to -0.94. Sorry, I don't know why these always get screwed up. And that should give us, so do this here, TCDF from -infinity up to -0.94 with 14 degrees of freedom, and we get a p-value of 0.18157 or 1.1816. And so they do have actually the number right down here, but this is wrong. And so with that p-value being greater than alpha, we can conclude, because the p-value of 0.1816 is greater than alpha, we fail to reject the null hypothesis. We do not have convincing evidence that the true mean DO level in the stream is less than 5 milligrams. So even though it was a little bit less, it wasn't significantly less. All right, so the second question asks us about our errors. Given your conclusion in part A, what kind of mistake or type 1 or type 2 error could you have made? Explain what this mistake would mean in context. And so in our case, since we failed to reject, we didn't find significant evidence. Maybe we should have. That's a type 2 error. So because we failed to reject, we could have made a type 2 error, failing to reject when the alternative hypothesis is true. If we did, then the true mean dissolved oxygen level in the stream is less than 5 milligrams, but we didn't find convincing evidence with our significance test. So that means we might, the stream might be at risk, but we aren't able to detect that. We go on we don't prove the null hypothesis is true, but we didn't find evidence, and so maybe we won't make any changes, and really your actions kind of a lot of times go on accepting the null hypothesis, even though that may not be the case. So exam tip, remember, if you just give calculator results with no work and one or more values are wrong, you probably won't get any credit for the do step. If you opt for the calculator only method, name the procedure, one sample t-test from you, and report the standardized test statistic, t of negative 0.94 degrees of freedom, 14, and p-value 0.1809. So you can do that in your calculator by doing stat over to tests. And then we are looking for the one sample t-test. And you might think, oh yeah, they're going to call it one sample t-test. No, they just call it t-test. All right, and you can type in the data or the statistics, and then you put in your null hypothesis, your x-bar, sample standard deviation, sample size, and then you choose what direction it's going to be, and then calculate. You can also draw a picture of the t-distribution, which is kind of neat.